Hey you guys, today we're starting chapter 6. It's a short, we're only going to do a few sections in chapter 6, and then we'll jump around a little bit. We'll take a test and get that done hopefully before Christmas. Okay, we've got 4 weeks. So get your notes, see what we got. Today we're going to talk about perpendicular bisectors, the word equidistance, distance from a point to a line, and then we have 2 theorems that we're covering. It's a perpendicular bisector theorem and an angle bisector theorem. Okay? So we have done this before, but we're going to review it real quick. The word perpendicular, we're going to talk about segments. This is always segments. And perpendicular, you write this symbol. Perpendicular, these 2 segments are perpendicular, which means the segments or lines form right angles, which is 90 degrees, right? So this is a 90-degree angle right here, and this one also is a 90-degree angle. That's what perpendicular means. Bisect means to divide into 2 congruent parts. So on this, we're talking about a segment bisector. So we're saying a segment equals a segment. So let's say we have segment AB, okay? And we're going to do the perpendicular bisector. So we're going through the midpoint, okay? So we'll call this M. We'll call this line L. Line L intersects segment AB at the midpoint. That's one thing that's true. It's perpendicular, so we've got right angles, okay? And segment AM is congruent to segment MB. Okay, let's put a point up here so we could talk about it that way. Let's call this C. So angle AMC, measure of angle AMC equals 90 degrees. Measure of angle BMC equals 90. Remember, the middle letter when you name angles is always a vertex. So all that stuff is true. You've got the perpendicular piece and the bisector. This is all about segments. Okay? Segment. Okay, now equidistant. You got the word equidistance. Equal distance. That's what the word means, equal distance. So, the word, let's jump to this real quick, distance from a point to a line. I've got a point, and I'm going to do line, and I'll call this line AB. Remember, you name points on the line, you do not name arrows. So this is line AB, this is point, this is a bad one, C. Okay, if I want to do distance, let's talk about distance real quick, okay? If I want to go how far is C from this line, am I going to draw this segment? Would that tell me how far the distance is? Am I going to draw this segment to find out the distance? Or am I going to draw the perpendicular segment and measure that length? And I think you guys know that. It won't be this segment. It won't be this segment. When I talk distance, it's always the length of this perpendicular segment to the line. okay? So when I want to know distance, I always have to see this perpendicular mark to know that this is a distance, okay? That would make sense in any kind of building, if you're doing any kind of construction, anytime you're measuring a length and you're finding how far you are from like a wall, you're always going to measure, you have to get that perpendicular, okay? So when we talk the distance from a point to a line, it's going to be the length of the perpendicular segment to the line. Okay, this, you're always look for the perpendicular symbol, okay? And that will be, you're talking, when we talk distance, you have to have that, okay? Equidistance means equal distance. Okay, now let's do the first theorem, okay? If a point lies on a perpendicular bisector of a segment, so this theorem is about segments. Okay, this is important that you understand that. So I've got a point that lies on the perpendicular bisector of a segment. Let's do this again. I've got a segment, we'll call it AB. I'm going to draw, let me get another color to help me, okay, just so I could see. I've got the perpendicular bisector, okay, just like we did up here. It's perpendicular and it bisects the segment. So I'm going to do the perpendicular bisector, okay. I'm going to have, so it's perpendicular and it bisects. So the length from, we'll call this M. The length from A to M is equal to the length from M to B. So I put the hash marks. M is the midpoint. So I'm perpendicular to segment AB, which means I'm forming 90-degree angles called right angles. And these segments are equal length. So I'm doing both things, perpendicular and bisect a segment. If that point is anywhere on here, I could pick a point up high, I could pick a point down low. If this point is anywhere on this perpendicular bisector, then the distance from, if I measure how far it is from the point to the end point, is going to be equal to the point to the end point. Okay? This distance, we'll call this C. If I pick any point on this red line, the distance from C to B would be equal to the distance from C to A. Then the point is equidistant to each end point. Okay? That point C is equidistant from A and from B, as long as it lies on the perpendicular bisector. So that means the length from C to A is equal to the length from C to B. Those lengths are equal. Okay? So now we're going to do the converse of this, and we're going to say first, if C is equidistant from the end points, then C must lie on the perpendicular bisector. We're switching this up. We're going to switch the hypothesis with the conclusion. Okay, switch hypothesis and conclusion, thus it's called a converse. So this time, if a point is equidistant from both segment endpoints, if, right, then the point lies on the perpendicular bisector of the segment. So this time I'm going to do the same thing. I've got segment AB, and I've got a point that lies on a line. We'll call this point C. This time, I'm not telling you that this line, L, is the perpendicular bisector. I'm not telling you that. I'm just telling you that this length equals this length. Okay? So if this length equals this length, if the length of, or the segment CA is congruent to segment CB, or you could say, get rid of these and say length CA equals length CB, then C lies on the perpendicular bisector of AB. And since I'm telling you that's true, that means that L is the perpendicular bisector. That means I have right angles and I bisect. Okay, that's your first theorem. Okay. The second theorem is a little bit different, and the pictures look similar, so you really have to pay attention. This time we're going to talk about angles, and we're bisecting an angle. So I'm going to have an angle. We'll call this angle A, the vertex B, another point on the other ray, C. Okay, and I'm going to tell you a point lies on the bisector of the angle. So I'm going to draw the bisector of the angle. If I'm bisecting an angle, I'm dividing the angle into two congruent angles. Okay, divide angle into two congruent angles. Angle equals angle. That's what a bisector of an angle does. So that means, let's call this D. Since I'm telling you it's a bisector, that means this angle is congruent to this angle. So ray BD, I'm telling you ray BD bisects angle ABC. Okay? Ray BD bisects. That means angle ABD is congruent to angle DBC. Okay? If all this is true, I give you this. This is what I'm giving you. I'm telling you that's true. Then here's what happens. The distance from D to one side, one ray of the angle, and D to the other ray, the other side of the angle, is the same. Okay, my picture's not great. Sorry. Okay? So if a point lies on the perpendicular bisector, then it is equidistant from both sides of the angle. So in this one, we're going to have distance equals distance. Okay? So if I draw, and remember when we talk about distance, we're talking perpendicular, okay? So these are the sides of the angle. That means if I draw this so it's perpendicular, this distance, if I drew my picture right, this distance, and then I'm going to draw this one so it's perpendicular, right? This distance, in order to show distance, I have to do this perpendicular to the side. That distance is going to be equal to that distance. So if D lies on the angle bisector, then the distance from D to one side of the angle is equal to the distance to the other side of the angle. So if I'm given bisector, and the point lies on the bisector, then I know the length from D to the side, okay, in this case, we're going to keep it those same points. Okay, then length AD is equal to length CD, okay? And when you look at this one, okay, these are your eyeballs looking, right? Look for the perpendicular to the sides of the angle. Okay, look for this right here. Look for this right here. Then you know you're talking about distance. Those two lengths are going to be equal. Okay, then I'm going to do the converse of this. Okay, if then we're going to switch the hypothesis with the conclusion, because that is what the converse means. So this time we're going to say if a point is equidistant to both sides of an angle, oh geez, then the point lies on the angle bisector. Okay? If a point is equidistant to both sides of an angle, then the point lies on the angle bisector. So this time I'm going to draw it a little bit. Maybe this will be easier to see if I draw it smaller angle. This angle is a pretty, what, maybe 100? Looks more than 90. It's close to 90. Try to draw an acute angle this time. Okay, and I'm going to tell you that this point right here, I'm going to tell you that this point is equidistant. Okay, I'm going to flip my paper. How's this? So it looks perpendicular. Okay, this distance equals this distance. I'm telling you that. It's perpendicular to both sides of the angle. Okay. Remember, distance from a point to a line. So I'm going from this point to this line, has to have perpendicular point to a line. If these distances are equal, then that means that this point lies on the angle bisector. So we'll say this is point C, this is point A, this is point B. So I'm telling you that A to C, that length equals C to B. Since I'm telling you that's true, that means that C lies on the angle bisector. Okay, which means then, because it's equidistant, that means that this ray is the angle bisector of the entire angle. Okay, that's it. Let's do a couple of these. So if you're looking for angles and you're looking for segments stuff, that's it. You have to decide, is it an angle, is it a segment? So in this question, it says find length RS. Now, when you're looking at these, they're almost all going to be part equals part. You just have to figure out which two parts. Okay? If I take this picture, look at it this way, I have segment PR, okay, and this is my segment bisector, okay? So it's a perpendicular bisector. So I could see from this that line SQ is perpendicular to RP. I've got that, and it bisects, okay? It's easier to see this way, but I'm going to turn it back, okay? So I've got segment SQ Q is the perpendicular bisector of segment RP. Okay? Since S lies on, I'm going to turn it again, okay? Since S lies on this perpendicular bisector, that means S is equidistant from both endpoints of the segment. So that means that this length and this length are equal. So since from S to P is 6.8, that means the length from S to R is 6.8. Okay, so that's what you're looking for. Looking for segment bisectors and angle bisectors. So this first one again, this time we're doing the converse. Okay, this is my segment, EG. Okay, this is my, I'm telling you H is equidistant from H is equidistant to G and to E. So you can see they're both 24. So this length equals this length. Since it's equidistant to both endpoints, this segment equals this segment, that means it lies on the bisector of this segment. So since this is 9.5, length EF is also 9.5. The question's saying length ES. There's no ES on there. So this has to be length EG. What is the length of EG? It would be 9.5 plus 9.5, which is 19. Okay? So we're going to look now at the next one, number 3. Then I'm going to stop. You guys got it. Okay, on this one, I've got segment AC. This is the perpendicular bisector. I've got the perpendicular symbol. So this is 90 degrees, 90 degrees. Length CB is congruent to the segment AB. Length CB equals length AC. So that means this is the perpendicular bisector of the segment, which means D, because it's on the perpendicular bisector, D is equidistant to both ends. Okay? Now, let's say we're bisecting, but it's not perpendicular, just for schnicks. Let's talk about that real quick so you see if you guys see it. If we said we're only going to bisect the segment, but instead of being perpendicular, I'm going to be at an angle that is not 90 degrees. If I were to do that, and I had D here, it's pretty easy to see. If D were right here, okay, let's put a D on here. If this were D, okay, the length from D to A, even though I'm going through the middle of the segment AC, I'm still going through the middle, but the length from D to A is shorter than the length from C to D, right? If I angled even more, right, this length and this length would not be equal lengths. If I stick this bisector and make the bisector perpendicular, now these lengths have to be equal. Okay, that's why you have to have perpendicular on this. If you don't have perpendicular, it's not going to hold true. Okay, so anyways, on this one, we're saying that D is equidistant from both endpoints. So this is still a segment equals a segment. Length equals length. Segments are congruent. Lengths are equal. So I've got length 5x is equal to length 3x plus 14. Most all of these are going to be part equals part. Now the question says find length of A to D. So I'm going to take my 7, I'm going to replace from A to D is equal to 5x, right? That's what this says. From length to A to D is 5x. So get rid of this x and put 7 right over it. When the 5 is mashed to the x, it's multiply. Length AD is 35. And that was the question. Okay, pencil's a bad idea. Sorry, you can't see it very well. Now, if I were to replace the x in this segment which is 3x plus 14, I should still get 35. So if I go 7, put the 7 in here for x, 7 times 3 is 21, 21 plus 14 is 35. So I still get 35, which I should, right? If a point lies on the perpendicular bisector of a segment, then it's equidistant from each endpoint. Okay, you guys, there you go. These are going to be the same ideas, except I'm telling you in words and you have to mark it. Okay, down here, now I'm looking at angle bisectors. I'm telling you J is equidistant from this side of the angle to this side of the angle. You know this because these are each 7 long. So J is equidistant from each side of the angle. Let's do like we did just a second ago. I'll call the point D instead. If this was my bisector, okay, no, this is just my, it divides the angle. Let's say we don't know if it's bisector. And I make it at an angle where the 42 is not equal to the 42, right? I'm telling you it's not. I'm telling you that this distance 7 and 7 are not equal. If they're not equal, right, then these angles won't be equal. But because this distance equals this distance, I know that segment FJ or ray FJ bisects. So that means this segment's congruent to this. So this angle has to also be 42. The question says, what is the measure of angle GF to J? Walk it and talk it. G to F to J, that's 42 degrees. Okay. This time we're talking about angles. These are all, we're bisecting angles. Up here, we're bisecting segments. I know the difference because we're talking about the distance from the point to the side of the angle. That's what I'm looking for. I'm looking for this. Okay. So there you go, you guys. Good luck. Hope this was helpful.